results of homology modeling methods have been getting better and better over time. And some of that is surely due to the quality of the methods themselves improving. But a lot of it is because of what's been happening in the PDB. So the era of fold discovery is long over. There's been many years since anybody reported a new fold. But people are still solving protein structures. So what's been happening is that coverage in general has been getting better and better and better. But also for specific proteins or families of proteins that are particularly interesting, there's been a lot of redundancy building up. So in general, it's becoming easier and easier to find templates. So here's what's been happening in terms of structures deposited. So the blue dots are the structures deposited for a certain year. And you can see here that actually oops, that's not a very good line. That actually looks kind of linear. That's not a good line either. Something like that. You can probably believe me if it looks somewhat linear to you, hopefully. And so every year there are more and more structures being solved. I'm sure there are a lot of reasons for that. I mean, of course, the technology is getting better. There's new cryo-EM methods. And of course, once one structure has been solved, people can just copy the protocol and solve the same structure again. Maybe at higher resolution, maybe with some different conditions, maybe slightly different sequence or whatever. But anyway, we're getting more and more per year, linearly more per year. And so the total number is just going to be the integral of this linear function, which is a quadratic function, right? So that's the cumulative number here, these orange dots. And to that, I've fitted a quadratic function. I think you would probably agree that if it's not perfectly quadratic, it's not far from being quadratic. So increased coverage means that you're more and more likely with time to be able to find a good template. So now it's even the standard basically to use multiple templates if you have them. Like Swiss model will use multiple templates, for instance, if it can find them. All the steps are automated. They're very nice online servers, which make it very easy for you to submit your sequence and get a very nice looking structure and a wonderful report and a very useful browser to sort of browse the sequence and the structure. So you really don't even need to know what's happening behind the scenes. But of course, it is good to know, for example, if you're just so you understand the method better and can choose your method to the application. Okay, so two examples as I mentioned. I really like Swiss model. It has this really nice sequence browser, so you can zoom in on specific residues and it'll tell you things about their secondary structure. And you can also get a little window where you can look at it in 3D. But there's also Modeler, which is also a very good program, and that's, I believe, the one you'll be using in the lab. I mentioned that there are no new folds being discovered, and there are not that many folds in total. So something like less than 1,000 folds available. Sequences, on the other hand, keep growing, pretty much probably exponentially still. And so that, there might be hundreds of millions of sequences. So there's a big incentive to discover good methods to match a sequence with an existing fold. So even if you can't find a homolog, you want to find which fold it would fold into. And so this specific problem of matching a sequence to a known fold where there is no sequence identity, this problem is called the problem of threading or fold recognition. And the earliest credible method for this was written by Bowie et al. In Science in 1991. They created something called a 3D 1D profile. So basically matched your amino acid sequence to a sequence of sort of environments, and we'll get into what that means. And since then, there have been updates, or not updates, but new methods which get a little bit more sophisticated and don't look at just a sort of a pairwise pseudo-sequence alignment, but rather they also look at how residues interact with each other in 3D, right? So you say, okay, well, these two residues have some sort of physical chemical compatibility, like maybe they have opposite charge, for instance, and they have a certain volume, and so this results in a certain probability of being seen together at certain distances, right? And so we'll talk about those methods a bit as well. Okay, but Bowie's profile method, the way it works is they took a library of folds, and then they classify each of the residues in those folds in this sort of 2D plot of buried area versus polarity. So if you are exposed to solvent, you're probably polar. You could be hydrophobic, but that's less likely because the surface of the protein is mostly composed of polar residues. Anyway, so the point is that you would be both polar and not buried, and so you fall into this class called E for exposed. And by the way, how do you measure things like solvent exposure? Well, you have your sort of your atoms, and let's say this on a surface of some protein. Then one way to do it would be to just roll a sphere that has a diameter, kind of like the diameter of a water molecule, and you roll it over this so that it gets to all the parts that are exposed to solvent, and then it calculates the area of that surface. And so that gives you the exposed area. And then the buried area, well, I'm sure there are a number of ways to do it. One way would be by Voronoi volumes, and so you add up the area of all these kind of planar boundaries between atoms. So anyway, so you need the area buried in this case, as opposed to the area that's exposed to solvents. So then if you go to if you have a residue that's partially buried, maybe it's kind of a little bit of it on the surface, but a lot of it has neighboring atoms, then you're in this region, which is P for partial, I guess. And if you're polar, then you would be in P2, and if you're sort of intermediate in polarity, then you would be in P1. And then, likewise, you could have a buried residue, something that's completely inside, let's say, like this, where it's no solvent exposure. Then you would be one of these classes, B1, B2, or B3. So if you're hydrophobic, which is kind of a likely case if you're buried, then you would be B1. If you're somewhere intermediate in polarity, you'd be B2, and if you're more polar, then you would be B3. Okay. And so what Bowie did was they computed this substitution matrix, which looks a lot like Blossom or PAM, because you see that you have residue types up here, but on this other axis you don't have residue types. You have environment classes, right? So you see the ones we just explained were B1, B2, B3, P1, P2, and E. And in addition, it further classifies it according to what kind of secondary structure they're in, whether they're alpha, beta, or other. And so the idea is that these all have substitution scores. So for example, if your target, your sequence of unknown structure, has, let's say, an I, then it has a certain probability of being buried in an alpha helix, right? So this is a positive number, so it's probably more likely to be in here than in other sorts of environments. And it's also kind of likely to be beta sheets and even coil, but in any case buried. It's a lot less likely to be exposed, right? So all these exposed environments, whether it's alpha sheet, beta sheet, or other, they all get negative scores, especially if for some reason it's very unlikely to be alpha helical, and I guess it's because it's beta branched. Okay, so it's kind of a nice exercise to sort of stare at this table and look for, sort of ask yourself, hypothesize what sort of residues you would expect in what sort of environments, and see if your intuition is correct. For instance, let's say, what would you expect for, let's say, lysine? Well, lysine is very polar, it's charged, so I would not expect it to be buried. So anything that's in B should have a negative score, my guess. Sure enough, these are all negative scores. It's very likely to be on the surface. In fact, I would even go further, and I would say it's likely to be on the loop on the surface. So exposed and, looks like I was wrong about that. So exposed and alpha helical has a nice, slightly positive score. Exposed and coil has a slightly negative score. Let's see, and one more. Let's say tryptophan. That's depends on the author. It's right on the boundary between hydrophobic and polar, but probably wouldn't really expect it to be on the surface. It does happen. But anyway, so surface exposed classes have negative scores, and it does pretty well here in the buried environments. Okay, so you might play with that and see if it's intuitive to you. So actually, let me go back just a bit. So basically, what you're going to do is you're going to get your target sequence, whatever that is, A, L, K, R, and then you're going to get your sequence of environments for a specific fold, right? And that could be, let's say it's B1 alpha, B1 alpha again, and then it switches to, let's say, I don't know, just making this up, B3 coil, and then it goes into P1 alpha, P1. Actually, this is not a very likely sequence, to be honest, but let's just say we're guessing. And so what you would then do is you would trace through this matrix using whatever algorithm you want, maybe Needleman-Wunsch, maybe Smith-Waterman. And then you would get a trace back, which would give you the optimal alignment between this sequence of amino acids and this sequence of environments. Okay, and so that would depending on what score you get, this would give you you pick the fold that maximizes this alignment score, and in addition, it gives you the actual alignment, so you can use that as a basis for homology modeling. But again, the point of threading is full discovery. Homology modeling is a different step. Okay. Now we talked a little bit about, or we mentioned that we have methods for computing a sort of a pairwise propensity, and the way it works is you can compute these. Yeah, sorry. You're going to end up sort of making an initial alignment, sort of like what we did already. But then once you have that, so let's say your fold looks kind of like this. And you got your target, and it kind of, you thread it through here, kind of like this, more or less. Now you're gonna know where all your residues are, and you know certain things about what sort of interactions you can expect between side chains, right? A positively charged side chain could interact very, very nicely with a negatively charged side chain. Two hydrophobics could interact very nicely with each other. Two negatively charged residues are not going to like being close to each other. And further, how close they like to be is not, even if they like each other, they don't want to be at zero distance. There's a certain equilibrium distance which has to do with the size of the side chain. And so that has led to these pairwise potentials between residue types. So here's one by Tobi and Alber. And what you're looking at is basically sort of a pseudo energy that's been inferred from the frequency at which these two residues are seen at that distance, right? And so here on the left you're seeing valine leucine, and you can see that's so basically what this is saying is that at this distance, let's say around something like 5.5 angstroms, these valine has been spotted. This distance residue for the case of valine leucine has occurred very often. So this is a distance that they're comfortable with. And if you look at this, 5 angstroms, maybe if you inspect add up the length of the side chains, you start to see that, oh yeah, well this is kind of like related to maybe not the sum of the maximum length of both side chains, but some sort of comfortable overlap in them where they're not too crammed together, where they might even be in danger of the backbones clashing, and not too far apart to where they're not in contact at all. So maybe 5.5 angstroms or so is about a sweet spot for this residue, or for this pair of residue types. So likewise, for phenylalanine tryptophan, well, what should you expect? Are these bigger residues? Yeah, these are bigger. I mean, tryptophan is very big. Phenylalanine is itself kind of big. And so you expect that this equilibrium distance to shift over to the right. And sure enough, there have been many observations of phenylalanine tryptophan at some distance, something around 7 angstroms. And so you can use Gibbs to transform frequencies into something like a pseudo energy. Okay. Sorry, I meant the Boltzmann equation. Okay, let's see. Right. So now we go on to 3D structure prediction and by ab initio methods, I should say. And by ab initio, I mean methods which only know about the sequence of your target. And so typically what we're talking about here is molecular dynamics. So what is molecular dynamics? So molecular dynamics is a physical but classical treatment of atoms in molecules. And so classical is that it's not quantum mechanical. Quantum mechanical treatments exist, but they're extremely expensive because you have to discretize the three-dimensional space for these electronic wave functions. And there are many electrons, and it's very, very many degrees of freedom. So you can only do it for very small molecules. So molecular dynamics, on the other hand, sort of rolls all these quantum mechanical effects into this semi-classical sort of treatment. And what it looks like is something like this. So you have so-called bonded and non-bonded terms, and then you have some way of dealing with solvent, right? So bonded terms mean things like bond stretching. So the way you're going to treat bond stretching is that you have some atom, let's say B and C, and you treat the bond as a spring, as a linear spring with some spring constant K. And you have some table that for each pair of atom types, you know what sort of, not only what the equilibrium strength of the spring is, what the spring constant is, but also what is the equilibrium length, the dead length of the spring. Then you have angle bending potentials. And so this is kind of like an angular spring, which has an equilibrium angle and some sort of spring constant, right? If this is an angular spring constant, let's just say it's kappa. I'm not sure if that's a good choice of letter, but anyway, let's just say that there's some sort of angular spring constant. And then, lastly, you can have torsion. And torsion is something that acts on 4 atoms which are covalently bonded, right? And so it gives you potential for rotations around this middle bond, right? And this is typically treated with some sort of harmonic. So if there's a single minimum, it would look like this, where this is your 360 degrees. If there are 2 minima, then it would look like this. It always has to be periodic, right? Because it can rotate and rotate and rotate again as many times as it likes. Or it can have 3 minima and so on, right? And so this potential looks like some sort of harmonic. And in addition to the number of minima changing, also the phase can change, like the location of these minima can change. And so we talked a bit about the conventions of how these, where's the 0 and so on for torsions. Let's see. And then we have non-bonded interactions, and so these atoms all have a partial charge assigned. In some cases, that partial charge might be very small. In some cases, it might be an integer. Well, maybe it's never exactly an integer, but at any rate, it could be. There's a variety of partial charges, and then of course they can have, in addition, an integer charge on top of that. So this acts not only between bonded atoms, but also between non-bonded atoms. So maybe like there's some additional atom out here, and these guys are interacting with each other, right? And you could have this, 1/r electrostatic interaction between them, right? So that could be very strongly attractive, or very strongly repulsive at close distances, and it starts to drop off after some time, after some distance rather. Then we have van der Waals interaction, which is an attractive interaction. It's an induced dipole interaction. The way van der Waals works is you have, of course, your positively charged nucleus, but there's a sense in which quantum mechanically there's some states which have the electron charge more sort of to one side of the atom, and there's a quantum mechanical sense in which, another atom nearby could also adopt a quantum state where the electrons are more on the other side, and this would be attractive, right? Because these electrons are kind of attracted to that nucleus, and these electrons are kind of attracted to that nucleus. And actually, this dipole that's emerging, it can also be switched the opposite way. And if they both switch to the opposite dipole, it'll still be attractive. And so there's a sense in which a dipole-dipole interaction is a superposition state of those two dipoles. We don't need to get too much into that, but the point is that this is exactly a 1/r to 6 potential. And but there are other interactions between two nuclei, or effectively between two nuclei, which are not as simple as this, and they all get rolled up into this R to 12 potential. Right. So there are things like the electron repulsion between the nuclei, which are again both positive. There's the when you compress the electron wave function, as you do when you try to push two atoms together, then the nuclear, the electronic wave function gets more, like the curvature gets larger, and that ends up meaning that it has more kinetic energy, and that costs energy. And there's also things like the centrifugal barrier, right, where if there's any angular momentum, then it requires energy to push them together. Right, because as push them together, they have to start to accelerate to maintain their angular momentum. Okay, so this actually ends up getting rolled up into this so-called Leonard-Jones potential. So Lennard-Jones is one way to approximate all the other pairwise atomic interactions in addition to the van der Waals. Okay, and then lastly we have something called solvation, and the sort of most direct way to consider solvation is to actually have explicit water molecules sort of surrounding your protein and solvating it, and that's the best way to do it in terms of accuracy, but it's also a bit slow. And actually, I take that back. There's some sense in which for some problems it's actually better not to model water explicitly. So mostly what people do is they start to play with things like the electrical permittivity. So they assign a different permittivity to the part that's inside the protein versus the part that's not in the protein. That's the solvent. And this sort of simulates the effect of these polar water molecules. And we don't need to get too much into that, but you should just know that there are explicit and there's implicit solvent. So explicit solvent is again when you have actual water molecules, you actually have their coordinates of all their atoms. And implicit means that you do things like change the electrical permittivity in this sort of segregated by zones. Okay, and so the idea is behind molecular dynamics as for protein folding is that you just drop this protein into this sort of simulation box and just watch the physics kind of let it fold. The problem is that this process is very, very slow, right? Why is it slow? Because the folding landscape is extremely complicated. There are very, very many degrees of freedom, and it takes time to explore all these degrees of freedom. And the upshot is that this has been shown to work, but only for very small proteins in very specific cases, right? So you have this problem of exploring this very complex folding landscape, and you might have seen this sort of so-called funnel, right? Folding funnel, and it's usually drawn as a cartoon. That's maybe in 2D, but the idea is that this kind of represents coordinate in some sense, and it could be a vector of coordinates. So here I'm showing one degree of freedom, but it could be it's basically 3 n degrees of freedom, where n is the number of atoms you have. And so this represents your protein, and let's say it finds some minimum nearby, like and it just falls into it. The problem with this is that this is a local minimum, but you would never know that there are other minima somewhere else that are even lower in energy, and so you have to keep exploring, and that means that you have to have some way or some algorithm for getting out of minima like this, for jumping over barriers which are unfavorable in hopes of finding a lower minimum nearby. And convergence is an issue because you will not know if you're converged or not because you don't know the right answer. So for any non-trivial protein, this search time becomes very, very long. And it's an open question of whether it would ever converge actually, because molecular dynamics brushes a lot under the rug. As we said, it doesn't explicitly take into account quantum mechanics, and so it could be that that in many cases this potential that you're trying to minimize would not actually converge to the right answer. And then you have to consider things like entropy. So it's not just about following energy to the minimum. There's also the sense that something that's enthalpically very low in energy might not be entropically very favorable. Like it might be very constrained. It might have very few degrees of freedom in its environment, and that might make something that looks enthalpically very favorable actually not be the right answer in terms of what the protein would fold into experimentally. And then there's a sense that the solution is not a single structure, but rather an ensemble. It jumps around to neighboring accessible states, and so there's that to consider. So it's a very hard problem, And like I say, now the momentum has sort of been shifting towards using neural networks rather than trying to explicitly use physics to fold a protein. Okay, so here's some empirical results of folding proteins using molecular dynamics. Here is actually a good result where you start out somewhere. Let's just say you start out here, and initially you had some high RMSD, right? Let's say this had something like 9 angstroms RMSD, which is not very good. And then you let the simulation run and run and run, and maybe you're doing lots of replicas with over many cores and for a very long time, and you start to fill up this phase space, right? And remember, you don't actually know the RMSD because in principle you don't know the right answer. I mean, you can as a scientist know the right answer, but just you don't tell your method, right? And you're just monitoring and see how close it gets to the right answer without giving any feedback about it. And the idea is that if this method is working correctly, then you're monitoring this energy. So this is energy. And you're looking for it to go down, 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 down in time as it starts to get closer and closer to the global minimum. And so at some point you're saying, oh look, I'm getting a whole bunch of structures that are in this sort of low energy region. And so I think those are more likely to be the correct answer. And in this case, sure enough, the very best of these is something between 1 and 2 angstroms RMSD from the right answer. And so this would be a case where the method is converging. However, maybe it's not converging perfectly, because you see here these blue dots here. You see those? That's using a starting structure that's actually the right structure. So you actually tell the right answer. You feed the protein already folded into this simulation box, and you let it run, and then it stays around that initial confirmation, which is different from the one you would have found sort of by fair means without telling it the structure. And so there's a sense that maybe the potential isn't quite right in terms of getting the perfect answer, or at least the experimental answer. But in this case, it was also not far. All right. So the other thing that's kind of promising about this was that once it isn't the right answer, then it kind of recognizes the right answer, because these blue states have lower energy than the black ones. So anyway, that would be a very good result, I think. On the other hand, that's not always what happens. In fact, more typically something else would happen. So here you're seeing another case where with time some low energy states were found. States that were clearly lower energy than the rest. And if you didn't know the answer, you might say, oh, look, I've converged. This is the right answer. But then you look at it, you look at the right answer and you realize, oh, it's completely wrong. This is something like 11 angstroms RMSD. And in this case, if you had started from the right structure, then it would stay around there. It would stay around the right structure. But there was no way, apparently, from this to jump all the way over here. Like I guess the barriers were just too high, and in terms of it never came to any structure that was close enough to where it could jump over to the right answer. Okay. And something that has happened some maybe 10 years ago. A number of groups started to report really good results for using something like mutual information to fold proteins. And so before we get into that, into exactly how that works, you should recall that, or actually, we haven't really done mutual information. We're going to do that in more depth once we get into RNA structure prediction. But the way mutual information works is you consider that residues that are adjacent to each other in space have to be compatible in some way. For example, hydrophobic residues might be compatible with other hydrophobic residues if they're in the hydrophobic core. Positive charge might be sort of compatible with negatively charged residues. They like to interact with each other. But the point is that if you change one of these two residues, the other one has to change also, right? So for example, if you have positive and negative, and this one changes to negative, then in any descendant of that organism, you'd have to change this one to positive. So now you have negative and positive, whereas before you had positive and negative. And so there's a sense of coevolution, where a change in one position induces a change in another position. And so if you have some multiple sequence alignment, it might have lots of, your whole sequence, whatever. Let's say you might find, let's say there's K, 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 and then R, 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 just to make kind of a cartoon example. And then at this position there's R, 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 and K, K, K. What it's saying is that when there's, oh, I'm sorry, I should have done this example, sorry. Let's say, let's say glutamate and lysine, and then over here, suddenly the lysine mutates to glutamate, and in those organisms, then you have to have over here a either lysine or maybe an arginine, right? And so the point is, a change here induces a change here, and so what do you infer? Well, you infer there's some sort of interaction between these two positions, right? And in the case of proteins, the signal will never be this clear, right? There's a lot more noise in it. And in addition, we have this problem of so-called indirect interactions, right? Because if you have some position 1, and it's interacting, like it's co-evolving with position 2, and then 2 is interacting with position 3, then there will also be sort of apparent coevolution between 1 and 3, but they're not actually in contact. See, the way I've drawn it here, like these two are actually close to each other, like they're actually touching, and 2 and 3 are actually touching, but 1 and 3 are not touching. But it could be very hard to disambiguate this interaction between 1 and 3, which is indirect, from the other two interactions, which are direct. And that's when methods based on DCA or direct contact analysis started coming to the fore, and these start to get much better results, right? So for instance, here you see that that mutual information sees an like some sort of interaction between these two residues, which is true, which is related to their being in contact, but then this one is co-evolving with everything else on this helix that it's on, and so that makes it look like this one residue is interacting basically with the whole helix, which it's not, right? And DCA suppresses this, and the way it does it is it's not explicit, it's implicit, and we're not going to get into math. It's actually reasonably complex, but the point is that it implicitly suppresses these indirect interactions in favor of the direct interactions, and then you start to get these results that look a lot more correct, and in fact people were able to fold certain proteins that way. But even that, I would say that in my experience, it's something that works really well when you have a lot of sequences, and it has to be a very high quality multiple sequence line, like maybe tens of thousands of sequences, then you start to get good results. For most cases, like even cases that are reasonably well studied, like let's say growth hormone, there you might have a few hundred sequences, and then the signal is just not there. So it's limited to cases where you have a very extensive and very high quality multiple sequence alignment. But that's not to say that's not important, actually, because number one, it's one of the inputs to the deep learning methods that have been getting really good success lately. And it's also another thing to consider is that the case of nucleic acids is very different. Like RNA has much more modular and specific interactions between bases, and for those, also they have a much smaller alphabet. And so for those two reasons, coevolution is actually very effective for predicting things like secondary structure. So with that, I'd like to cut it off, and then you'll also be watching Arna's lecture on the use of deep learning for protein structure prediction. and I'll see you in the discussion section.